In the depths of World War II, along the shattered landscape of Western Europe, American forces faced an enemy that seemed almost invincible, not because of the soldiers defending it, but because of the structures themselves. The German military had spent years, decades even, perfecting the art of fortification. They had poured concrete by the millions of tons, reinforced it with steel that could withstand the heaviest artillery bombardments, and created defensive positions that turned every advance into a nightmare of casualties and stalled momentum. Traditional explosives would shake these bunkers, crack their outer walls perhaps, but rarely did they achieve the kind of catastrophic destruction needed to neutralize them completely. The thick concrete, the interlocking fields of fire, the machine gun positions that could sweep entire fields clean of advancing infantry. All of these made the German bunker network a fortress that seemed to laugh at conventional weapons. American commanders, watching their men die by the hundreds trying to take a single fortified position, knew they needed something different, something that didn't just explode, but fundamentally destroyed the very material that made these bunkers so deadly. They needed a weapon that could attack the structural integrity of steel and concrete in a way that high explosives simply could not achieve. The answer came in the form of a chemical reaction so intense, so devastatingly hot, that it represented a completely different approach to warfare. This was thermite, a mixture that when ignited, could reach temperatures of approximately 4,000 degrees Fahrenheit, hot enough to melt through steel like a blowtorch through butter, hot enough to turn the very building blocks of German fortifications into rivers of molten metal. The thermite grenade was not just another explosive device in the American arsenal. It was a fundamental reimagining of how to attack hardened positions, a weapon that used chemistry and extreme heat rather than shockwaves and fragmentation. To understand why this weapon became so crucial, why it represented such a significant advantage for American forces pushing through France, Belgium, and into Germany itself, we need to understand the nature of the enemy fortifications. We takes to never of the enemy fortifications. The science behind thermite and the desperate tactical situations that made such an extreme weapon not just useful, but absolutely necessary. The German philosophy of defensive warfare had been refined through brutal experience. In World War I, they had learned the value of concrete and steel, of positions that could absorb punishment and keep fighting. By the time World War II erupted, this philosophy had evolved into something far more sophisticated. The Atlantic Wall, the Siegfried Line, the countless bunkers and pillboxes scattered across occupied Europe, these were not simple concrete boxes. They were engineering marvels in their own right, designed by military architects who understood exactly how to maximize defensive advantage. A typical German bunker would have walls several feet thick, made from reinforced concrete that incorporated steel rebar in complex patterns to distribute force and prevent catastrophic failure. The firing ports were narrow slits that offered minimal target area to attackers while allowing defenders to sweep wide arcs with machine gun fire. Many bunkers were interconnected by tunnels, allowing defenders to reinforce positions or escape if one section became untenable. They were often partially buried or built into hillsides, using the earth itself as additional armor. The entrances were offset, protected by chicane and additional walls that prevented direct fire into the interior. Ventilation systems allowed them to be sealed against gas attacks. Some of the larger fortifications had multiple levels, ammunition storage, medical facilities, and supplies to withstand siege conditions for weeks or even months. When American forces landed in Normandy in June 1944, they immediately confronted this defensive network. The initial assault had to overcome beach fortifications that had been specifically designed to stop amphibious invasions. Every bunker on those beaches had been positioned to create overlapping fields of fire, meaning that attacking one position exposed you to fire from 2 or 3 others. The casualties were horrific. Even after the beaches were taken, every mile of advance through France meant encountering more fortified positions. The hedgerow country of Normandy was bad enough, with its ancient earthen walls and sunken roads that turned every field into a natural fortress. but combined with German concrete and steel positions, it became a meat grinder. American infantry would assault a bunker, pour rifle and machine gun fire against it uselessly, call in artillery that would crater the ground around it, but leave the structure intact, and then have to resort to desperate close assault tactics that cost lives with every attempt. The standard approach to bunker assault was brutal and straightforward. Infantry would lay down suppressing fire, trying to keep the defenders from manning their weapons effectively. A squad would try to maneuver close enough to throw grenades through the firing slits, an approach that required getting within a few meters of positions, specifically designed to kill anyone who got that close. Flamethrowers could sometimes force defenders out, or kill them through oxygen depletion, but flamethrower teams were priority targets, and the weapons themselves were dangerous to operate. Engineers would try to place satchel charges of explosives against walls or doors, hoping to blow a hole large enough to assault through, but even large explosive charges often just cracked the concrete without actually breaching it. Tank destroyers and tanks with high-velocity guns could sometimes knock out bunkers if they could get a clear shot and had armor-piercing ammunition. But bunkers were usually positioned where they had clear fields of fire against approaching armor, and the narrow firing slits were incredibly difficult targets to hit. The Germans knew all of these tactics, had trained against them, and had designed their bunkers specifically to defeat them. This is where the fundamental problem became clear. High explosives work through shock waves and fragmentation. When a grenade or artillery shell explodes, it creates a sudden expansion of gases that produces a pressure wave moving outward at supersonic speeds. This pressure wave can kill through overpressure, rupture organs, collapse lungs, but against thick concrete and steel, it just transfers force. Concrete is actually quite good at absorbing and distributing that kind of force. The steel reinforcement helps it flex slightly and return to shape rather than shattering. Fragmentation, the pieces of metal casing that turn into deadly projectiles, could wound or kill exposed soldiers but did nothing against reinforced walls. You could drop a 500-pound bomb on a well-built bunker and maybe collapse part of it, maybe kill the defenders through concussion, but you might also just crater the earth around it, while leaving the structure fundamentally intact. What was needed was not force but heat, not explosion but melting, not shock but a sustained chemical reaction that could attack the very molecular bonds holding steel and concrete together. Thermite had been known to science since the late 19th century. The basic principle was elegantly simple. Take a metal oxide, something like iron oxide, which is essentially rust, and mix it with a pure metal powder that has a stronger affinity for oxygen, typically aluminum powder. When you ignite this mixture, what happens is not an explosion, but an incredibly vigorous oxidation reaction. The aluminum atoms desperately want oxygen, and they pull oxygen atoms away from the iron oxide with such violence and speed that enormous amounts of heat are released. This is an exothermic reaction, meaning it produces heat as a byproduct, but the amount of heat is staggering. The temperature of burning thermite reaches approximately 4,000 degrees Fahrenheit, some formulations even hotter. At this temperature, iron melts completely. Steel, which is mostly iron with carbon and other elements added, also melts. Concrete begins to break down as the water bound in its structure explosively converts to steam, and the cement itself starts to calcinate and crumble. The military potential of thermite had been recognized before World War II. The Germans themselves had used thermite incendiary bombs during their bombing campaigns, particularly the fire raids against British cities. These were not designed to melt through steel but rather to start uncontrollable fires, and they were devastatingly effective at that purpose. The concept of using thermite as an anti-structure weapon, something that could be delivered by infantry at close range, was a natural evolution but one that required solving significant technical challenges. Pure thermite mixture is not easy to ignite. It requires a very high temperature to start the reaction. typically achieved through a magnesium ribbon fuse or a similar ignition source that can provide the necessary heat. Once started, the reaction is essentially unstoppable. It does not require air to continue burning because the oxygen comes from the metal oxide in the mixture itself. You cannot extinguish thermite with water. In fact, adding water can make things worse by creating explosive steam and in some cases hydrogen gas. The thermite will burn underwater, in a vacuum, in any environment, until the chemical reaction is complete. The American military adapted thermite technology into a hand-delivered weapon system. The ANM-14TH3 incendiary grenade became the standard thermite grenade used by American forces. This was not a fragmentation grenade, not something you threw to kill enemy soldiers through blast or shrapnel. The casing was thin sheet metal designed merely to contain the thermite mixture until ignition, after which it would burn through almost immediately. The grenade contained about 2 pounds of thermite mixture, enough to sustain a burn for approximately 40 seconds. Although the peak temperatures and most intense melting occurred in the first 10 to 15 seconds. The fuse system used a standard grenade fuse pull pin and safety lever, but instead of a timed explosive detonator, releasing the lever triggered a starter mixture, typically a combination of magnesium powder and barium nitrate, that would burn hot enough to ignite the main thermite charge. The soldier using one of these weapons had to understand that once you pulled the pin and released the lever, you had a few seconds to deploy it before the starter mixture ignited, and once ignited, the thermite itself would burn through the grenade body almost immediately. The tactical employment of thermite grenades against German bunkers required a combination of courage, tactical skill, and understanding of the weapon's capabilities and limitations. You could not simply throw a thermite grenade at a bunker from a distance and expect results. The grenade had to be placed in contact with, or very near the steel and concrete you wanted to destroy. This meant getting close enough that you were well within the defensive fire zone of the bunker, close enough that machine gun fire could cut you down in seconds. The assault teams that carried these weapons were often volunteers, men who understood the risks and accepted them because they also understood that taking out a bunker meant saving the lives of dozens or hundreds of their fellow soldiers who would otherwise have to assault across open ground under fire. The typical attack sequence began with suppression. Every weapon that could be brought to bear would fire at the bunker, not expecting to penetrate but forcing the defenders to keep their heads down, to hesitate before exposing themselves at the firing slits. Mortars would drop smoke rounds to obscure the approach. Rifle grenades might be fired to keep the defenders disoriented. Under this covering fire, the assault team would move using every bit of cover and concealment available, working their way close to the structure. The approach was the most dangerous part. German defenders knew what assault teams were trying to do and would put out maximum fire to stop them. Machine gun bursts would chew up the ground. If the bunker had supporting positions, they would add their fire. Men would be hit, would fall, but the survivors kept moving, because stopping meant dying just as surely as advancing. Once at the bunker wall, the tactical situation changed completely. The firing slits could not depress enough to target someone pressed right against the exterior wall. This created a dead zone, a tiny area of relative safety directly against the structure. The problem was getting into that dead zone without being killed, and then staying alive long enough to employ the thermite grenade effectively. Some bunkers had been designed with this exact situation in mind, with overhead positions or adjacent structures that could fire down on anyone who reached the wall, but many older positions lacked this feature. The assault team member with the thermite grenade would pull the pin, release the lever, and then had to make a crucial decision about placement. The most effective position was on top of the bunker roof if it could be reached, where the thermite could burn down through the concrete. The alternative was to place it against a firing slit, wedging it so the thermite would burn directly into the interior, or against the door if the bunker had an accessible entrance. What happened next was both spectacular and terrifying. The thermite ignited with a brilliant white light, so bright it was painful to look at, directly hot enough that anyone within a few feet could feel the radiant heat like standing next to a blast furnace. The metal casing of the grenade burned through almost instantly, allowing the thermite mixture to flow, and flow it did, like a small river of liquid sun. The temperature was so extreme that steel reinforcement bars in concrete would begin to melt within seconds. The concrete itself would start to spall and break apart as water in its structure turned to steam with explosive force, as the cement matrix began to break down chemically under temperatures it was never designed to withstand. If the thermite was burning through a roof, molten metal would drip down into the interior of the bunker, setting fire to anything flammable, forcing defenders away from their positions or outright incapacitating them if they were caught by the dripping thermite. The heat inside a closed bunker would become unbearable within seconds, the air itself seeming to burn, temperatures rising so high that breathing became difficult. If the thermite had been placed at a firing slit, the effect was even more direct and immediately lethal. The burning thermite would pour directly into the bunker interior, a stream of 4,000-degree material that would ignite anything it touched, melt metal, burn flesh, and create conditions that were simply unsurvivable. The defenders had very few options. They could not extinguish the thermite. Water would not work. Trying to move it would result in severe burns. The heat and smoke would be overwhelming. Their only real choice was to abandon the position immediately if they wanted to survive, and bunkers were specifically designed to have limited exits, which could easily become blocked or dangerous to use under combat conditions. Many defenders faced with a thermite attack would choose surrender rather than face the inferno inside their once impregnable fortress. The psychological impact of thermite grenades extended far beyond their immediate tactical effect. German defenders who had survived a thermite attack, or witnessed one, would lose confidence in their fortifications. The concrete and steel that had seemed so protective, that had made them feel safe even under heavy artillery bombardment, could be defeated by a single soldier with a specialized grenade. This knowledge spread quickly through defensive positions, bunkers that might have held out for days, forcing Americans to bring up heavy weapons, or bypass them, would now surrender much more quickly when faced with assault teams known to carry thermite weapons. The weapon created a psychological lever, a way to crack the morale of defenders who might otherwise have fought to the last man in the belief that their fortifications gave them an insurmountable advantage. The effectiveness of thermite grenades was not uniform across all situations or all bunker types. The weapon had limitations that tactical commanders had to understand and work around. Thermite works through sustained contact and heat transfer. Against a bunker, with extremely thick walls, multiple feet of reinforced concrete, a single thermite grenade might not achieve full penetration. It would still cause significant damage, still create heat and smoke issues inside, but might not completely neutralize the position. In these cases, multiple grenades might be needed, or the thermite attack might be used to soften the position for follow-up attacks with conventional explosives. Weather could also be a factor. Heavy rain would not extinguish burning thermite, but it could cool surfaces more quickly and might reduce the overall effectiveness of the heat transfer. The greatest limitation was always the delivery problem, the need to get close enough to place the grenade effectively, which remained dangerous no matter how good your suppressing fire was. The development and deployment of thermite grenades represented a broader shift in American tactical thinking during World War II. The American military had entered the war with doctrines and weapons based largely on World War I experience, updated and modernized but fundamentally similar in concept. The reality of combat against German fortifications forced rapid innovation and adaptation. Thermite grenades were part of a larger toolkit that included shaped charge weapons like the bazooka, flamethrowers, white phosphorus grenades, and specialized engineer equipment. Each weapon addressed a specific tactical problem. The bazooka could engage bunkers from longer range, but required a clear line of sight and good marksmanship. Flamethrowers were devastating but short-ranged and made the operator a priority target. White phosphorus created smoke and had incendiary effects, but did not generate the sustained extreme heat of thermite. Thermite grenades filled a crucial niche, providing infantry with a weapon that could defeat hardened positions through chemistry and heat rather than explosive force. The science behind the thermite reaction is worth examining in detail to understand why it was so effective. At the molecular level, the mixture contains iron oxide molecules, where iron atoms are bonded to oxygen atoms, and pure aluminum atoms in powder form. The aluminum is more reactive than iron, meaning it has a stronger electrochemical attraction to oxygen. When sufficient heat is applied to start the reaction, aluminum atoms begin pulling oxygen atoms away from the iron. This electron transfer releases energy in the form of heat. The heat released causes more aluminum and iron oxide to react, which releases more heat, creating a self-sustaining and rapidly accelerating reaction. The products of this reaction are pure molten iron and aluminum oxide, also known as corundum, which is the same material that forms rubies and sapphires. The molten iron at 4,000 degrees is hot enough to flow like water and will burn through most materials it contacts. The aluminum oxide slag is also molten and extremely hot, adding to the overall thermal effect. The temperature of 4,000 degrees Fahrenheit needs to be understood in context to appreciate its destructive power. The melting point of iron is approximately 2,800 degrees Fahrenheit. Steel melts at similar temperatures depending on its carbon content and alloying elements. This means thermite burns at temperatures well above what is needed to melt steel, creating a margin that ensures rapid melting. For comparison, the surface of the sun is about 10,000 degrees Fahrenheit, so thermite gets you nearly halfway there. At these temperatures, most organic materials do not just burn, they essentially vaporize or char instantly. Wood, fabric, rubber, leather, all the materials that might be found inside a military fortification would ignite immediately if touched by thermite, or even if exposed to the radiant heat from close by. Human tissue exposed to these temperatures would be destroyed essentially instantaneously. Even the radiant heat at a distance of several feet would be severe enough to cause burns. The tactical situations where thermite grenades proved most valuable were the close quarters fights that characterized much of the European campaign after D-Day. The fighting through the Norman hedgerows involved clearing countless small fortified positions, often just reinforced machine gun nests, built into the hedgerow embankments, but still requiring close assault to neutralize. The urban combat in French, Belgian and German towns and cities presented endless opportunities to fortify buildings and create strong points that commanded key streets and intersections. The Siegfried Line, the main German defensive fortification along their western border, was a dense network of bunkers and dragon's teeth obstacles that had to be reduced position by position. Later, the fighting in Germany itself, as American forces pushed toward the Rhine and beyond, involved attacking fortified towns and cities where every substantial building had been turned into a defensive position. In each of these contexts, thermite grenades gave American infantry a capability they desperately needed. Consider a typical scenario: a reinforced concrete bunker built into a strategic hilltop, commanding a road that American armor and vehicles need to use for their advance. The bunker is small, maybe 15 feet on a side, walls 3 feet thick, housing a heavy machine gun and a crew of 4 to 6 soldiers. Traditional artillery strikes have failed to destroy it. Tank fire has only chipped the concrete. An infantry assault across open ground would result in dozens of casualties as the machine gun cuts down anyone who approaches. The American company commander calls for a volunteer assault team, 4 men, carrying rifles, grenades, and 2 thermite grenades, prepare to move. Supporting squads lay down suppressing fire, hundreds of rounds per minute, directed at the bunker's firing slits. Mortar teams drop smoke shells to obscure the approach route. The assault team moves in short rushes, using shell craters, and the terrain folds as cover. German fire probes through the smoke, random bursts hoping to catch movement. One assault team member is hit, goes down, The others keep moving, because stopping means death. They reach the dead zone against the bunker wall, pressed flat against concrete still warm from artillery strikes. One soldier pulls the pin on a thermite grenade, lets the lever fly, counts to 3, then scrambles onto the low roof of the bunker and places the grenade on top. He rolls off the roof and takes cover as the thermite ignites. The white-hot flame burns straight down. Molten metal begins dripping through cracks in the concrete. The machine gun falls silent. Shouts from inside the bunker. German voices raised in panic. Smoke begins pouring from the firing slits. Within 30 seconds, the bunker door opens and the defenders stumble out, hands raised, faces black with smoke, willing to surrender rather than die in the heat. The position that might have held up an entire company for hours or days has been neutralized in minutes by 4 men and a specialized grenade. This scenario, with variations, played out hundreds of times across the European theater. Each time, the thermite grenade proved its value not just as a weapon, but as a tactical problem solver, a tool that turned seemingly impossible situations into manageable assaults. The production and supply of thermite grenades involved industrial chemistry on a massive scale. The United States had substantial capacity for producing both aluminum powder and iron oxide. Aluminum production had expanded enormously to support aircraft manufacturing, and iron oxide was essentially a refined form of rust, available in huge quantities. The mixing of the thermite composition required care, as the powder needed to be fine enough to react quickly, but not so fine that it became dangerously prone to accidental ignition. Quality control was essential. A thermite grenade that failed to ignite properly or burned too slowly would be worse than useless. It would endanger the soldiers, who had risked their lives to place it. The grenades were manufactured in the United States and shipped to Europe as part of the enormous logistics operation that kept American forces supplied. They were distributed down to the company and platoon level, with units that expected to face fortified positions receiving priority for these specialized weapons. Training soldiers to use thermite grenades effectively required both classroom instruction and practical exercises. Men needed to understand what the grenade could and could not do, how to place it for maximum effect, how to coordinate with supporting fires, and critically, how to survive the experience of getting close enough to a bunker to deploy the weapon. Training grounds in England, and later in France, would include mock bunker the fires have made, structures where assault tactics could be practiced with dummy grenades. NCOs and junior officers who had successfully used thermite grenades in combat would share their experiences, teaching the hard-won lessons about approach routes, timing, and placement. The psychological aspect was also important. Soldiers needed to overcome the natural fear of closing with a fortified position that was actively trying to kill you, needed to trust in the weapon and their training, needed to have confidence that the thermite would do its job once deployed. The German response to American thermite weapons evolved as the war progressed, and they became more aware of this capability. Some bunkers were modified to include overhead protection, specifically designed to prevent access to the roof, making placement of thermite grenades more difficult. Defensive positions began to include more interlocking and mutually supporting fields of fire, so that even if assault teams reached the wall of one bunker, they would still be under fire from adjacent positions. Some defensive doctrine emphasized more aggressive close-range defense, using grenades and submachine guns to engage assault teams before they could get close enough to deploy specialized weapons. However, by the time these adaptations were being implemented, the strategic situation had shifted decisively against Germany. The industrial capacity and manpower to thoroughly upgrade defensive positions across all fronts simply did not exist. Many positions remained vulnerable to thermite attacks throughout the war. The broader impact of weapons like the thermite grenade on World War II and subsequent military development should not be underestimated. These weapons represented a recognition that modern warfare required specialized tools, for specialized problems. The era of a general-purpose infantry weapon, being sufficient for all situations, was over. Infantry squads needed anti-tank weapons, anti-fortification weapons, smoke and illumination devices, communications equipment, and specialized ammunition types, all in addition to their standard rifles and machine guns. This specialization continued and accelerated after the war, leading to the combined arms teams and specialized combat engineer capabilities that characterize modern military forces. The specific technology of thermite grenades remained in various military arsenals for decades after World War II, used in Korea, Vietnam, and other conflicts wherever fortified positions needed to be defeated at close range. The human cost of bunker warfare and the deployment of weapons like thermite grenades deserves acknowledgement. Every fortified position that had to be assaulted represented a moment of extreme danger for infantry soldiers. The men who carried these weapons into combat, who exposed themselves to enemy fire to place grenades that could melt steel, showed extraordinary courage. Many did not survive their assault. Others were wounded, burned, or traumatized by the experience. The defenders inside bunkers faced their own nightmare, trapped in enclosed spaces as thermite burned through their protection, having to choose between burning to death or surrendering. War is brutal regardless of the weapons used, but close quarters combat against fortified positions represents some of the most intense and terrifying fighting imaginable. The thermite grenade, while effective, did not make this fighting easy or safe. It simply made it possible to succeed without even higher casualties. As World War II progressed into its final year, the accumulation of tactical innovations like thermite grenades, improved infantry tactics, better coordination between infantry and armor, and overwhelming firepower superiority began to tell decisively. German defensive positions that might have held indefinitely in 1940 or 1941 were being overrun in hours or days in 1945. The Siegfried Line, built to be impregnable, was breached and broken. The Rhine was crossed. German cities fell to Allied forces. Throughout this final campaign, thermite grenades and similar specialized weapons played their part, giving infantry the tools they needed to reduce fortifications and continue the advance. Each bunker destroyed, each pillbox burned out, represented one less obstacle between the Allied armies and final victory. The legacy of the thermite grenade extends beyond its immediate military application. The weapon represented a triumph of applied chemistry, an understanding that sometimes the best way to defeat a physical obstacle is not through force but through exploiting material properties and chemical reactions. The temperatures achieved by thermite, the sustained heat that could melt steel and destroy concrete, demonstrated principles that would later be applied in metallurgy, welding technology, and industrial processes. Military engineers learned valuable lessons about the vulnerabilities of fortifications, lessons that influenced post-war defensive construction and also informed the development of new weapon systems. The shaped charge, which uses explosive force to create a focused jet capable of penetrating armor, operates on different principles but shares the concept of attacking material properties rather than relying solely on blast effect. In examining the story of thermite grenades destroying German bunkers, we see a microcosm of the larger war. American industrial might produce the materials. American ingenuity developed the tactical application. American soldiers carried these weapons into impossible situations and made the impossible happen. The seemingly impregnable fortresses of concrete and steel that had dominated the defensive landscape of World War II could be defeated by chemistry, by heat, by a reaction that turned aluminum and rust into molten iron at 4,000 degrees. This was warfare not just of guns and explosives, but of science and chemistry, of understanding material properties, and exploiting weaknesses that conventional weapons could not touch. The bunkers that had protected German defenders, that had seemed so solid and permanent, were revealed to be vulnerable to a weapon that could melt their steel bones and crack their concrete shells from the inside out. The thermite grenade stands as a testament to necessity, being the mother of invention. Faced with fortifications that resisted conventional assault, American forces developed and deployed a weapon that changed the tactical equation. The price was high, paid in the lives and wounds of soldiers who had to get close enough to use these weapons, but the alternative would have been even higher casualties and potentially stalled advances that could have prolonged the war. In the calculus of warfare, a weapon that could turn an impregnable position into a death trap, that could force surrender or abandonment through sheer thermal destruction, was worth its weight in gold. The thermite grenade burned bright and hot, melting German steel and breaking German morale, one bunker at a time, helping write the final chapters of World War II in rivers of molten metal and the white-hot fire of chemical fury.